Hello, I am Sahan Salpage from the Hansen Research Group here at Florida State University. I am here to briefly introduce our recent findings published in the Journal of Chemical Communications titled Wavelength Selective Separation of Metal Ions Using Electroactive Ligands. Before I begin, I would like to pay my sincere admiration to my fellow co-workers Ronald, Yan, Jamie, Tom, and my advisor Ken for their unparalleled contribution to this project. There is growing interest and demand in search of novel approaches for separation of metal ions for reasons of both cost and public safety. For example, efficient and cost-effective purification of water and treatment of the existing radioactive waste could play a vital role towards sustainable use of resources. However, existing methods including transmutation, ion exchange, and redox chemistries have often fallen short when it comes to the separation of metal ions that have similar chemical properties such as charge density, size, and binding affinities. As a much needed intriguing alternative, a separation method that relies on photophysical properties instead of the chemical nature of the metal would serve a great purpose in that regard. Here, we report a novel photochemical separation strategy that relies on irreversible chemical transformation of the coordinating ligand rather than the nature of the metal ion. In a nutshell, a ligand, in this case a terpyridine functionalized with a redox-active benzene disonium group acting as an electron acceptor, is bound to the ruthenium metal ions in solution. Then these complexes were excited with the 455 nanometer LED to initiate the photo-induced electron transfer from the metal center to the functionalized ligand, which causes an irreversible reduction of the disonium moiety into hydrogen atoms. The process of this transformation was monitored by UV-Vis spectroscopy. The ground state spectrum at time equals 0 showed two characteristic Rho-terpy absorption features with peak absorbance located around 289 nanometer and a broad MLCT band at 518 nanometer. Upon excitation, blue shifted absorption spectra were observed with a new absorption maxima observed at 284 nanometers and 493 nanometer, suggesting the removal of the charged disonium moieties. To analyze the kinetic aspect of the transformation, experimental absorption decay data was fitted using SpecFit software package. The theoretical fit shows a two-step transformation from the starting disonium complex A to the final product C. Moreover, data suggests that the entire transformation goes through a short-lived intermediate species B, presumably as a partially reduced complex with one disonium group. The concentration profiles of A, B, and C obtained from SpecFit shows an exponential decrease of A and simultaneous growth of intermediate B. During the course of the reaction, the concentration of B was diminished and the final product C became more predominant. The ruthenium disonium complex was synthesized as follows. An aniline functionalized terpyrinyl ligand was synthesized in 4 steps using commercially available starting materials. The ligand reacted with ruthenium chloride in refluxing ethanol, followed by isolation as a hexafluorophosphate salt by adding excess potassium hexafluorophosphate. Then two aniline moieties were oxidized to benzene disonium with sodium nitrite in hydrochloric acid and isolated as a hexafluorophosphate salt. The ruthenium disonium complex was characterized by proton and carbon NMR. The proton NMRs of starting ruthenium disonium and reduced product after the photoreaction are depicted here. In ruthenium disonium NMR, proton signals HA and HB are de-shielded due to the charged neighboring disonium moieties and as a result shifted more downfield. However, in the product NMR, we can see significant shifts due to the reduced disonium. Proton signals of HA and HB are now shifted more upfield, located around 7.75 and 8.2 ppm respectively. The new triplet signal that appeared at 7.7 ppm is due to the HH that resulted from the loss of the disonium after the photoreaction. To demonstrate the wavelength selective separation, an equimolar mixture of ruthenium and iron disonium complexes, denoted as C, was excited using a 455 nanometer LED. This promotes the excited state electron transfer of ruthenium disonium from its MLCT band, which leads to the subsequent reduction of the disonium acceptors. Irreversible reduction of the disonium moieties results in the formation of chemically altered ruthenium terpy, leaving most of the iron disonium unharmed, as depicted in F. Absorbance profile of before and after 455 nanometer light exposure clearly shows significant blue shifting of the MLCT band of ruthenium compared to that of iron. Likewise, excitation into the iron MLCT band with 700 nanometer light initiates the electron transfer from the iron center to the disonium acceptor. Absorbance profiles of before and after 700 nanometer light show significant blue shifting of the MLCT band of iron compared to that of ruthenium. In both cases, reduced and starting complexes were easily separable via chromatography. Thus, the method offers a revolutionary photoselective technique for the separation of metal ions. In summary, we developed a novel photo-based separation technique to speciate metal ions by using the redox properties of benzene disonium. As a proof of concept, we successfully utilized this technique to separate iron and ruthenium mixtures at two different wavelength excitations. The photoreaction proceeded through a short-lived intermediate to give off the fully reduced complex. The differences in polarity between the initial and reacted complexes were used to separate two metals by means of chromatography. This opens the door to an entirely new separation strategy that does not rely on the solubility or binding affinity of the metal ion, but instead on the intrinsically unique absorption spectrum of the metal complexes and the properties of the reacted ligand. Research is underway to investigate the oxidative aspect and extend this strategy to enable the separation of inner transition metals. We hope that narrow absorption profile features of lanthanides and actinides could provide an unique method to separate species with similar binding affinities, thus providing a viable option to treat nuclear waste stockpiles. Finally, I would like to pay my sincere gratitude to our wonderful group led by Professor Kenneth Hansen, and last but not least, the DOE for their financial support. If you need more information about the CAST EFRC, please visit our website at cast.magnet.fsu.edu. You can follow us on Twitter and Instagram for our newest research updates. Thank you for your attention.